SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course, that is Power Plant System Engineering, Module 4. The title of this module is Hydro and Renewable Energy Power Generation System. So, previous lectures we have emphasized about the hydro energy part. From now onwards, we will focus our attention to renewable energy systems. So, the first category of renewable energy system is the wind energy. So, in this lecture, we will emphasize on some specific topics. First, let us see that what is this renewable energy resources and why wind energy falls under this category. Then we will see what is the impact of wind energy in the recent days. So, we will try to see what is the energy potential that can be achieved through wind. Then we will try to understand the fluid mechanics principles for harnessing wind power, and then to have this wind power we require some machines and we call them as wind machines or wind turbines. Now, when these wind turbines are installed at a particular geographical locations, we must understand about its structural stability. That means, the fluid mechanics way of analysis of calculating forces on wind turbine blades. So, these are the topics of discussions in today's lectures. Now, let us go one by one. So, the first point that I need to emphasize is that renewable energy resources. In recent days, energy has been basic necessity for the existence of mankind, and in every sectors, and in fact in all developing countries, every sectors requires the role of energy, such as agriculture, industry, residential and in the commercial farms. So, since the energy demands are very huge, the conventional energy resources is not sufficient to meet these demands. Hence, we need to explore other category of energy resources. So, nature has given us the plenty of opportunities, and based on that we can classify them as conventional sources, or we say that non-renewable energy resources. Other category is non-conventional resources or renewable energy resources. So, by considering this, we have to see that when you say use the word renewable, it is essentially the energy is formed by nature itself. So, in other words, the way we consume our energy or the rate at which we consume the energy must be generated by the nature itself. So, in such cases we classify those energy resources as renewable form of energy. So, one point of time conventional sources of energies was thought to be renewable maybe 200 years back, because demands are less, but energy formations are more, resources are available in plenty. But with recent days, the fossil fuel based energy resources has shown sharp decline, hence they fall under the category of non-renewable sources of energy. Then as of now, what are the renewable sources of energy that we are going to quantify and try to see if they have some potentials to meet the today's energy needs. So, essentially the classification of energy resources are of two types: conventional sources, non-conventional sources. Under the conventional sources, we have commercial or non-commercial. Commercial category have coal, petroleum, natural gas, then electricity, they are fall under commercial requirement. In non-commercial category, we have firewood, straw, dried cow dungs, and those are the non-commercial form of energy. But that part we have already discussed at the time of discussing about the steam power plant, where coal was the major source of energy. But now our attention will be more focused towards the renewable source of energy. Under these headings, we have bioenergy, solar energy, wind energy, tidal energy, energy from urban waste, and geothermal energy. We will try to touch upon in subsequent lectures and in this module some of these energy resources. Now, let us understand very specific what is this renewable form of energy, which means that nature creates this energy on its own, and the rate at which nature produces it, it also can be when it is consumed, the rate at which it is consumed is much less than the rate at which it is burned. So, that is the way we call this as renewable energies are clean, they are abundant resources and continuously reproduced by the nature. They have the capability of self renewing the resources. And under these headings we have sunlight, wind, flowing water, biomass and earth's internal heat. As you see in this figure, in this solar energy we have solar cells or solar photovoltaics, we have wind means wind machines, wind turbines, hydro we have power plants, geothermal, that is another category of harnessing energy from earth resources or earth crust, and bioenergy, which is mainly derived from bio derived plants. Then we will move on to this wind energy, and before you go for the theoretical background, let us see whether this wind energy has sufficient potential or not. So, as you see in this figure, over the last 25 years, there is a steady growth in the requirement of wind energy as a supplement for other resources of energy. Now, with last 25 years, the steady growth shows that wind has a tremendous potential in supplementing the main or primary energy resources. Moreover, since the energy abundant, clean, cheap, and it can be also supplement the major conventional energy resources as a mainstream electricity generations, the wind has a immense potential which can be considered as the next generation's demands. So, with a projection by Indian International Energy Agency, the roadmap says that about 25% of global energy demand will be made by wind energy by the end of 2050. So, that means we must try to understand the capability of wind as a potential renewable energy resources. So, having said this, let us try to understand why this wind forms. Why we say it have, although we normally know that wind is the flow of air, but why this air flows? So, essential background for the wind formation is that the solar heatings. So, sun is the major resources of energy. When the sun's radiations falls on the earth's surface, then it falls as well as on lands as well as in all water bodies. So, the very basic difference between these that is that when it falls on the lands, the land gets heated. So, what happens? The air associated with the ground or land mass also gets heated. So, once this gets heated, its density drops. So, it blows, it moves up. On the other hand, when it falls on the water bodies, some of the radiations gets absorbed by the water itself and some gets evaporated from the water surface. So, that way the evaporated waters goes to the up. So, basically speaking, as you know that evaporation causes cooling. So, they normally when they gets evaporated, they tries to supplement the heated air which is on the ground. So, because of this temperature difference between the water bodies and land mass, the air tries to move from higher density medium, which is the water, to the lower density medium, that is land. So, in this process the wind blows or air flows, so we call it as a wind. Now, in general there are two types of winds, one is planetary wind, other is the local wind. So, if you look at this particular figure as I mentioned earlier, so we have a cool surface, warm surface. So, cool dense air comes down and warm light air goes up, because warm means its density is less. So, air moves up. So, that is what this circulation keeps on happening, and the convection and advection currents tries to supplement each other. Now, looking at the wind, the first category of wind we call this as a planetary winds. So, if you look at this earth, so this planetary wind comes from the effect of rotation of earth, and the solar heating falls on the entire earth mass. So, entire earth mass constitutes of water bodies as well as land mass. Now, looking at the earth surface, if you can say we have a equator somewhere in the middle of this earth, and we have north pole and we have south poles. So, eventually the region, that is hot air regions, is mainly falls on the equator area, and the cold air regions are north pole as well as south pole. So, what happens when the sun's radiance falls on the earth surface, and at the same time earth is rotating on its own axis as well as the sun. So, eventually we all know that the equator regions gets the enough solar radiations. So, that means air becomes hotter. So, this hot air moves up and goes to the upper atmosphere, and it tries to float towards the north pole or south pole, and we call this as a air movement from equator to poles. Side by side, when it goes in that directions, it pushes the cooler air in the vicinity of earth surface, and they try to move towards equator, and such solar heating causes the planetary winds. In fact, one becomes cool surface, other becomes hot surface. So, dense air cools on the surface itself, whereas hot air moves in the upper atmosphere. So, this is we call it as a planetary winds. Other kind of winds that we call as a local winds. So, local winds is essentially at one particular location. If you want to see, there are water bodies as well as land mass. So, as you refer this figure, we have water bodies here and we have land mass, and even during we have daytime as well as the night times. So, what happens, let us try to see that when sun's radiations falls on both these land mass and water bodies, eventually what happens, this when the sun's radiation fall on the water surface, some of the water vapors gets evaporated. So, that means it goes to the atmosphere, but that is replaced by the hot air that comes from the land mass. So, this circulation keeps on happening, because hot air has a less density, it flows towards the water medium at little bit higher altitude, and finally it comes and replaces the cool air. So, thereby the circulation happens, air heated over the land keeps rising, and this warm air they gets cooled in the upper atmosphere and keeps descending. Then this cool air of water bodies again comes back to the land. So, whatever heated air, it is again replaced by this cool air that comes from the water bodies. So, this particular concept happens in the daytimes. So, exactly reverse phenomena operates in the night time, where normally we have warm air that comes from water, they are being replaced by air mass that comes from the land. So, this phenomena normally we call this as a land breeze, when cool air from land flows towards the warmer water bodies, and other term we use at the sea breeze, when wind blows from water bodies to warmer lands. In the second mechanism of wind formations, we have hills, and because of this landmass in the form of hills, now because of the slopes of these hills, air above the slope heats up during the day and cools down in the night more rapidly than the lowlands. So, because of this, the heated air during the day keeps rising along the slopes and relatively cool air flows down during nights. So, this is what we call as a elevation difference that causes the wind blowing or air motion, and we call this as a wind. So, having said these wind formations, we have now a standard survey shows that about 2% of solar radiation falling on the earth's surface is converted to kinetic energy in the atmosphere, and 30% of this kinetic energy occurs at the low elevation, that is within 1 kilometer above earth's surface. Now, if it is possible to harness this 30% kinetic energy of this air, which is normally happens at lower elevations, that it can satisfy the energy requirements of any developed countries. So, because of these reasons, wind power has a compelling positive arguments for as a potential resources for future energy generations, and moreover it is they are pollution free and also they are available in free. Now, let us understand what is the fluid mechanics principle of wind power. So, to harness wind energy, we require some structure and we call that as wind machines, and as you refer this particular figure, this is the schematic view of a wind machines or typically called as wind turbine, and it is installed at a particular geographical locations, and depending on the size we can fix its area, what is called as swept area. That means, we are capturing the wind which is available at any geographical locations. So, based on the area which is perpendicular to the wind directions, we call this as a swept area, and considering this area, we can imagine to have a stream tube passing through these turbines or propeller. So, typically why you call as a propeller, because turbines are connected to some shaft and rotor arrangements, that means wind drives this propeller. Now, there are two things, one is wind which is available if you take a particular segment, that is from A to B, in which the turbines are or wind machines are installed, and another free stream area that is starts from I and E, that is inlet and exit. So, this is the entire domain in which we are bothered about the location of the wind machines. So, wind flows at some velocity Vi and pressure Pi, and that is the we can say inlet, and wind leaves from the turbines far away from this location, that is from B, point B. So, we call this as a, and its pressure is Pe and Ve. Obviously, what is going to happen about the pressure and velocity distributions, one can simply apply these Bernoulli's equations. So, initially when the wind approaches towards the turbine, so initial pressure keeps rising and suddenly entire energy gets converted to power. So, pressure suddenly drops from Pa to Pb. So, ideally or hypothetically it could be from it will be sharp drop, but eventually what happens, it drop in pressure from Pa to Pb is not exactly sharp, it is a inclined straight line. Whereas, we do not see the same way the pressure drops, but the velocity drop takes place in a gradual manner and it starts dropping from A to B. So, essentially between the location of A and B, we have the turbine installation or wind machine installations. So, power is being harnessed at these locations. So, because of this reason, pressure and velocity drops. Now, eventually when after point B, the wind starts gaining its further momentum and try to expand, and because of this region pressure further increases, but velocity becomes final velocity Ve, and that is nothing but your exit velocity. So, there are three velocities, one is inlet velocity of the wind, exit velocity of the wind, and there is a velocity at which the rotor rotates, and that is called as turbine velocity Vt. And in fact, for a given wind speed, we have a fixed value of Vt. So, we need to find out what is the relation between Pa, Pva, Pb, Vb, and if at a particular stream velocity Vi, what should be the value of Vt. So, this is the essential theme of this what we call as principle of power generations. So, essentially speaking, the outgoing exit streams must have less pressure and velocity, because that will give you the maximum wind potential in this captured area. And in these zones, wind kinetic energy will be maximized for rotation of the rotor or shaft. So, we need to understand the mathematical expression for this complete domain. So, we take this complete domain as I and E, that is inlet and exit, and location A and B as the location at which the turbine is being installed. And so, we are, since at these things there is a drop in the pressures, we will keep aside A and B separately and try to apply Bernoulli's equations between I and A, one equation, other is between B and E. So, based on this, we write these general energy equations from I to A and B to E. So, we write, and we also, of course, we also neglect the elevation difference. So, we say Pi plus half rho Vi square is equal to Pa plus half rho Va square. Similarly, Pe plus half rho Ve square is equal to Pb plus half rho Vb square. And here we assume this density of air to remain constant, because it is a flow is incompressible. And as you see from this figure, since Vi is greater than Va, Vb is greater than Pb, so which implies that Pa should be greater than Pa and Pb is less than Pa. Now, from these two equations, we can get an expressions between pressure difference between A and B in terms of initial pressure, exit pressure, initial velocity, exit velocity, and pressure difference between A and B, velocities between A and B. And here we will try to impose some assumptions, and which is more realistic way of estimating. So, for example, if you assume that Pe to be is equal to Pi, that means we give a sufficient domain, so that the wake effects of wind that goes out from the turbine will not affect the main free stream wind. So, for that reasons, we allowed this velocity drop to gradually, and it finally matches with the free stream. And similarly, pressure drop is also happens to be in a gradual manner, and finally it becomes Pe. So, since there is no wake effects, then we can make an assumptions that Pe approximately equal to Pi, and Va and Vb, they are also approximately equal, and that part is essentially is nothing but your turbine velocity. That eventually happens this location at which the wind turbine or wind machine is installed. So, with these assumptions, we get an expressions for pressure difference between A and B, we call as Pa minus Pb, that becomes half rho Vi square minus Ve square. Now, next thing is that we, from these expressions, we need to find out the what is the axial force. The axial force is nothing but the force that is being experienced by these wind machines due to this pressure difference captured over the swept area A, and we can write this as Pa minus Pb times A, and this expression was also becomes equal to half rho A into Vi square minus Be square. So, this is one way we find this axial force through this pressure difference. Other way of calculating this axial force is through mass flow rate of the turbines. So, if you normally the force is nothing but rate of change of momentum. So, rate of change of momentum is nothing but mass times velocity difference. So, this velocity difference is nothing we can find from initial velocity and the exit velocity, and mass flow rate is rho times A into Vt. Vt stands as the velocity of the turbine. So, we have two expressions for axial force in two different forms. one is through Newton's law, other is from the energy equations. So, by equating both of the thing, both the equations, we get an expressions. The turbine velocity Vt is nothing but half summation of Bi plus Be. So, once we know Vt, then next job is to find out what is the steady flow work, and work is nothing but the difference in the kinetic energy, that is W into half rho Vi square minus Be square, and when you multiply this into mass, that is m dot, it will give you the total work. Now, from this work transfer we can get the steady flow power, and that becomes P is equal to m dot by 2 into Bi square minus Be square. So, m dot we have already expressed from these expressions. Inserting this m dot here, ultimately we will end up having the power expressions P is equal to 1 by 4 rho A into Vi plus Be whole multiplied by Vi square minus Be squares. So, you have to pause your attention right now here, because we have to find out which are typically constants. So, from these expressions we can say that rho is a constant quantity, does not change from this entire domain between I and A. A is the swept area, that is fixed by the installation locations. Bi is your wind speed at that particular location, but that we do not have any controls, but our job is to maximize the wind kinetic energy. So, only control that we have is the Ve. So, eventually if you can reduce this Be as small as possible, then this negative term will come down. So, that means we need to bring down this Ve term, because it kills the main power. To do that mathematically, we have to differentiate dP with respect to dVe, and we get a quadratic equations, and from this we obtain the optimum exit velocity is equal to Bi by 3, and putting this value B optimum value, we get this maximum power P max is equal to 8 by 27 half into rho A Vq. So, this is what we get the power from these turbines. Let us find out what is the total power available in the wind. So, that is nothing but half m dot into Vi square, and this turns out to be half rho A Vq. Now, if you take this ratio between these two terms, we call it as a maximum efficiency of the turbine or maximum power coefficient, that is we call as eta max, which is nothing but P max by Pt, and from this simple expression it turns out to be 16 by 27, or it is 0.593. So, this number is a very significant term, that maximum efficiency that can be captured by any turbine does not exceed beyond 59.3%. So, means that any turbine's efficiency cannot go beyond this number. So, this is a particular limiting case, and this comes out from theory, and it is a fixed number, and since it is comes from a theoretical analysis, then none of the turbines can harness a power coefficient more than this number. So, that is the things we call this as a this particular number is most familiarly known as Bayes number, or we put this limit as Bayes limit, which does not exceed 59.3% or 0.593. So, for all wind turbine analysis, Bayes number is the most or optimum number that any turbine cannot approach. So, that we call this as a ideal propeller type turbine. Now, there are two efficiency, one we have already explained as the maximum efficiency, but any realistic turbine, if you want to find out, we can write its efficiency of the turbine as eta is equal to instead P by Pt, and here this efficiency normally range from 30 to 40%. So, conventional wind turbines have range in this range, and at the same time there are many possible ways, and we also define another term which is called as a tip speed ratio. Lambda is equal to omega times r by Vi. Omega is the rotational velocity of the turbine, r is the radius of the turbines. So, if you look at this turbine rotor from the tip, the velocity varies drastically because the structure is huge. So, we call this as a tip to speed ratio. Now, considering this, we depending on the location or installed structures, the tip speed ratio can vary. It can vary with R, depends on the rise of the rotor. It can also vary with respect to Vi, that is initial wind speed, or it can also vary with the rotation of the rotor. So, that is the reason this lambda, which is known as tip speed ratio, is plotted against the efficiency term. So, for a theoretical number, as a theoretical number, this lambda is a fixed number, that is efficiency approach to the Bayes limit 0.593. So, we call this as a ideal propeller type turbine. Now, any other realistic type turbine that we operate in a particular locations, they are classified as horizontal axis turbine, HAWT, vertical axis turbine, and any kind of rotors we call as 7S rotor, and we can have multi-blade type rotor. So, and all these are nothing but the wind machines, but if you can see here, they have different numbers in terms of the tip speed ratio. For example, this multi-blade type of rotor can have tip ratio close to maximum 1.8, but if you look at vertical axis Darius type of wind turbines, they can go up to a tip speed ratio close to 7.5. So, this is how we can vary, and in fact, when you go for higher efficiency range, then we can explore horizontal axis, high speed horizontal axis wind turbines. So, depending on the particular geographical locations at which this wind is available, the choice of rotor or turbines can be done. So, this analysis gives the more realistic view for applying wind machines at a particular locations. Another important point that I need to emphasize here, that the power coefficient is strongly dependent on to blade to wind speed ratio that reaches maximum value at about 0.6 only at the maximum speed, and the blade speed drops rapidly with blade tip to wind speed ratio, which is below 2. That means, if you take this particular multi-blade type rotors for which you have tip speed ratio does not exceed 1.2, then you can see efficiency at a particular point drop drastically when the tip speed ratio is less than 2. The next important analysis that we are going to discuss in the same wind power philosophy is that analysis of forces. So, in a particular type of propeller type wind turbines, there are two forces that acts. One is the circumferential force, which is in the direction of wheel rotations, and in fact, it generates the torque for the rotor, and that for which electric power generation is possible. Another part or force, which is nothing but your axial force, that is generated due to wind stream, and this force, that means your turbine structure must withstand this axial force for harnessing the power. So, this particular axial force does not lead to any power production turn, rather our structure should withstand this axial force to harness the power from the wind. So, this gives the structural stability of the structures of the wind machines, and for which axial force needs to be evaluated. Now, all this analysis we must do at the maximum point of efficiency or optimum exit velocity. So, for that reasons, let us try to understand what is the torque developed by the turbines, that is P times omega. It can be also represented in terms of RPM of the rotor. So, the torque can be expressed in terms of this, because we know power term, we know area. So, we can express the torque. Now, at maximum efficiency, that is eta max is equal to 16/27. So, maximum torque can be simplified with this number, and again we can find out the what is the axial thrust on the turbines, which is derived from our earlier expressions, and it is expressed in terms of diameter of the rotor, initial wind velocity and exit wind velocity, and at maximum efficiency point we can get Fx max, that is maximum axial thrust, in terms of diameter, that is pi by 9 rho times d square into Vi square. So, these two terms are very vital, one for torque generation other for maintaining the structural stability. So, this is all about the wind theory. So, of course, another important point I need to emphasize here is that referring to these particular expressions like F max is pi by 9 rho d square into Vi, one can minutely observe that this maximum thrust is proportional to the square root of diameter. So, that means if your normally this diameter is or the swept area is kept very large to capture more wind power, but at the same time while enlarging this diameter your axial thrust also goes up. That means we need a heavy structure to withstand to harness this wind power. So, two ways, that means one has to make a balanced approach, and that what is the balanced design approach, that what is the maximum structure that we can install based on the wind speed, available wind speed at that particular locations. So, for that reason the upper limit diameter is determined through appropriate design by ensuring the stability of this structure and other economical considerations. Of course, geographical site location is also more important. So, this is all about the contents that I need to deliver in this lecture. So, based on our content, let us try to solve a numerical problem based on our analysis, that is principle of wind power. So, the problem statement goes like this. It is a simple problem. The average wind speed at a particular geographical location is 8 meter per second and conditions, and it is at a standard atmosphere. That means we know pressure and temperature at that locations. So, based on this we need to calculate the total power density, then which is available in the wind with respect to this 8 meter per second. Then we need to find out the maximum power density which can be obtainable from wind turbine, that is through Bayes limit. Third is what is the realistic density obtainable from a horizontal axis wind turbines. So, in that location if you want to put a wind machines, and that is nothing but a horizontal axis wind turbine, then you need to assume certain efficiency. To assume certain efficiency we can refer this particular curve, that if you take a particular horizontal axis wind turbine, typically their efficiency, average efficiency falls as 0.4. So, that is what we say it is a realistic power density corresponding to this efficiency. And same location if you use a vertical axis, probably efficiency may come down below 0.4. So, in this case we can say realistic power density, for which you can say efficiency can be treated as 0.4 or 40%. Then we need to find out the total power produced by 100 meter wheel diameter. That means, if that horizontal axis wind turbines has wheel diameter of 100 meter, then you have to find the total power. Now, for this total power, what is this and what will be the maximum thrust and torque when the turbine rotates at 40 rpm and at maximum efficiency point. So, for all these things we have derived this established formula. This problem also explains that how you are just introduce that formula and keep calculating. So, let us understand what is the data given, which is Vi is 8 meter per second, and atmospheric conditions we say P is equal to 1 atmosphere or 101,325 Newton per meter square. Temperature can be assumed to be 15 degree centigrades or 288 Kelvin, and since it is for air we take R as 287 joule per kg Kelvin. So, keeping ideal gas equation we can find out the density of air, rho is equal to P by RT. So, this turns out to be 101,325 divided by 287 into 288, and it is 1.23 kg per meter cube. So, the first expression, what is the total power density? So, total power density we say it is P total by A, and that becomes half rho Vi Q. So, we know rho, we know Vi. So, this number turns out to be 315 watt per meter square. Second term, we say what is the maximum power density, that is P max by A, putting Bayes limit, and that is 8 by 27 rho VIQ. So, this number turns out to be 186.6 watt per meter square. Third term is realistic power density, that means we need to find out P by A, instead of, that is nothing but efficiency into P max by A, and efficiency was taken as 40% for a horizontal axis wind turbines. So, this term becomes 0.4 into 186.6. So, this is 74.6 watt per meter square. Next term, we say what is the total power produced from a 100 meter turbine wheel. So, for that we can say, if you take D as 100 meter, so P can be calculated as, and that you can say A is equal to pi by 4 D square, and once we know A, we can calculate P is equal to A times 74.6, and this number is 602 kilowatt. And next term is torque and axial thrust at operating speed of 40 rpm. So, N is your 40 rpm. Then we can find out expression for T max. So, T max expression goes like this, that is 2 by 27 rho D VIQ divided by N. So, rho is given, D is given, N is 40 rpm, that is 40 by 60 revolution per second. So, this number becomes 2 by 27 1.2 into 100 into 8 Q divided by 40 by 60. So, T max is close to 7 kilonewton. And last term is what is maximum axial thrust, Fx max. So, this expression can be is written as pi by 9 rho d square Vi square. So, by inserting all the numbers, we say 275 kilo Newton. So, let us try to understand the physics behind things. So, to produce a power of 600 kilowatt by a wheel diameter of 100 meter, we are able to get a maximum torque of 7 Newton. That means, for that torque, we can say for the structural stability, we need to, the structural stability of that wind machines or horizontal axis wind turbines will have ability to withstand a force of at least 275 kilonewtons. So, wind turbines sizes are big. So, it is more requirement for wind turbine study is that we need to also understand the structural stability of the machines that at a particular locations. With this, I conclude. Thank you for your attention.